Since its inception, the Earth has been bombarded by asteroids and comets, which have frequently caused large mass extinctions, such as that of dinosaurs, so these celestial bodies can rightfully be considered the most dangerous for our planet. The impacts of large asteroids or comets on Earth are also at the center of the plot of many fantasy films, such as Armageddon, Deep Impact, or the more recent Greenland. Let's have a look at their most notable characteristics. Asteroids are small stony things found mostly in our solar system's main belt, between the orbits of Mars and Jupiter, and thus between 2 and 3 astronomical units from the Sun. Remember, an astronomical unit is the average distance between Earth and the Sun. Aside from the main belt, there are other populations of asteroids, such as the Trojans, which orbit Jupiter at the Lagrangian points L4 and L5. Lagrangian points, named after the Italian mathematician Giuseppe Luigi Lagrange, are points of gravitational equilibrium that correspond to stable configurations in which three bodies can remain in equilibrium in the absence of external perturbations for an indefinite time. In the case of Jupiter, the two Lagrangian points L4 and L5, which contain the Trojan asteroids, form an equilateral triangle with the Sun and the planet, putting them on the same orbit as Jupiter at an angular distance of 60 degrees from the planet. There is still an outer asteroid belt, known as the Edgeworth-Kuiper belt, located between 30 and 50 astronomical units from the Sun, and hence beyond Neptune's orbit. Asteroids, on average, travel in orbits that are slightly inclined on the ecliptic plane, the plane of the Earth's orbit. To date, there are about 100,000 asteroids with precisely known orbits, with an even larger number of additional objects awaiting more extensive observation in order to extract a more trustworthy value of the orbital parameters. There are only 26 bodies with a diameter greater than 200 kilometers. The rest are smaller, up to a few meters in diameter. Comets are small icy bodies that travel in very elongated and inclined elliptical orbits on the ecliptic plane. When they approach the Sun, solar heat and radiation heat the small icy nuclei, increasing the pressure of the trapped gases inside them. These gases then escape, breaking the surface crust of the cometary nucleus and producing jets of dust and gases that the comet leaves behind, forming the two tails, the ion tail, produced by the interaction due to the decreasing of the strength of solar radiation. The comet moves away from the Sun after perihelion, and the activity of its nucleus declines until it ceases. When the Earth's orbit around the Sun passes through the deposits of dust left by comets, these particles enter the Earth's atmosphere and burn by friction with the Earth's atmosphere, producing meteors, which many of you will surely have observed during the hot summer nights. The Perseids of August, the Leonids of November, and the Geminids of December are among the most famous meteor showers. Comets are classified into two types based on their orbital period: short-period comets, which take less than 200 years to complete a revolution around the Sun, such as Halley's Comet, which has an orbital period of 76 years, and long-period comets, which take more than 200 years to complete a revolution around the Sun, such as the spectacular C/2020 F3 Neowise, which has an orbital period of 6,688 years. Short-period comets are thought to come from the Edgeworth-Kuiper belt, while long-period comets are thought to come from the Oort cloud, the outermost portion of the solar system extending up to 100,000 astronomical units and likely holding 200 billion ice cometary nuclei. Comets and asteroids are scientifically fascinating because they supply us with significant information about the genesis and evolution of the solar system. They are thought to be the remnants of planet formation. According to the most widely accepted theory, the solar system formed about 4.5 billion years ago as a result of the gravitational contraction of a nebula of gas and dust. At the time, it was a rather turbulent place, because the same planets were formed by aggregation of matter as a result of violent impacts, which produced innumerable rocky debris that has been preserved until today in the form of asteroids and comets. Is it true, however, that all asteroids and comets pose a threat to our planet? Actually, only NEOs pose a threat to the Earth. NEO is an acronym that stands for Near-Earth Objects, and it refers to the population of entities that orbit around the Sun on trajectories that could collide with the Earth. Given that asteroids, comets, and thus NEOs are celestial bodies with negligible mass in comparison to the Sun or planets, it is very likely that their orbit will be perturbed by the gravitational attraction of this one, making it very difficult to predict their future orbital evolution. There are around 20 NEOs with diameters higher than 5 kilometers, such as the one that is thought to have triggered the extinction of the dinosaurs 65 million years ago, another 1,000 with sizes between 1 and 5 kilometers, and even 150,000 with diameters greater than 100 m. For two reasons, the risk of impact with a NEO larger than 1 kilometer is highly uncommon in the framework of natural disaster threats. 1. The impact's repercussions are significantly higher than those of any previous natural or man-made disaster, even nuclear war. 2. The likelihood of such an occurrence occurring throughout a human lifetime is exceedingly low. To attempt to quantify the risk of a NEO impact on Earth, the Turin scale was launched in 1999 during the Impact International Conference on the NEO problem held in Turin, Italy, with 11 steps ranging from grade 0, 0 probability of collision, to grade 10, maximum collision probability on a global scale. In theory, grade 0 has no meaning. Grade 1 demands constant object control. Grades 2 to 4 necessitate extra attention and maybe intervention studies. Grades 5 to 7 are regarded disturbing and necessitate action planning. Grades 8 through 10 depict safe collisions that necessitate action. Let's go over each step in detail now. Grade 0, the likelihood of a collision is 0 or so low that it is regarded as 0. This class also includes small objects that burn in the atmosphere, such as meteors and fireballs, as well as infrequent meteorite falls that rarely cause damage. Grade 1. The item makes a close pass through the Earth, but does not pose an unusual amount of risk. The likelihood of a collision is exceedingly low. The news does not deserve to be brought to the public's attention. New observations will almost certainly result in a grade 0 reassignment. Grade 2. The item makes a close, but not altogether extraordinary trip to the Earth. While it demands astronomers' attention, there is no need to bring the news to the public's attention because the likelihood of a collision is extremely low. New observations will almost certainly result in a grade 0 reassignment. Grade 3. The object has a near approach that warrants astronomers' attention. The calculations indicate a 1% or higher likelihood of an impact capable of causing only limited destruction. Grade 4. Similar to Grade 3, however, the destruction would be on a larger scale. Grade 5. Close approach with an item that offers a substantial but still unknown threat of regional disaster. Astronomers must pay close attention to this to determine whether or not the collision will occur. If the flyby is slated to occur within the next decade, government plans to reduce the threat must be in place. Grade 6 is similar to 5, but if the flyby is scheduled for fewer than 3 decades, the government must guarantee threat reduction plans. Grade 7. A close contact with a huge object, which could happen this century, offers an unprecedented but still undetermined threat of world catastrophe. For such an event to occur this century, international emergency plans must be put in place, particularly to establish whether the collision will occur immediately and with confidence. Grade 8. The collision is certain, but the destruction will be on a small scale. These occurrences occur between 1 to 50 times every 1,000 years on average. Grade 9. The collision is certain, but the devastation would be on a regional scale. These occurrences occur once every 10,000 years to once every 100,000 years on average. Grade 10. The collision is unavoidable, but it will cause worldwide devastation, endangering humanity's destiny. These occurrences occur no more than once every 100,000 years on average. Finally, consider the potential defenses against the danger of collision with a NEO with a diameter higher than 100 m. NASA and other space organizations have proposed essentially two approaches, deviating the NEO off its trajectory or destroying it. Several strategies have been considered to achieve these goals. Let us look at a few of them. Nuclear strategies centered on the use of powerful thermonuclear charges to deflect or destroy a NEO on a collision course with the Earth. Their great advantage is the enormous energy released, about 1 million times that of traditional explosives. It has been calculated that, in order to disturb the speed of NEO of 1 centimeter per second with dimensions of 100 m, 1 kilometer, and 10 kilometers, explosive charges with energies of 0.1 to 1 kiloton, 0.1 to 1 megaton, and 0.1 to 1 gigaton would be required. For comparison, the energy released by the nuclear devices of Hiroshima and Nagasaki is, aside from the danger of radiation, the disadvantage of nuclear techniques is that the results are difficult to control. There is always the risk that the asteroid will fragment into several blocks still aimed at the Earth, and the problem will be multiplied rather than solved. Kinetic energy transfer. The main idea is to have the NEO on a collision course with the Earth impact in a certain direction with a large mass bullet. The problem is that this mass would be too large to provide enough energy to a NEO with a diameter of 1 to 5 kilometers in order to impart the necessary thrust to deflect it. A projectile on the order of 1,500 tons would be required. This is an unusually large mass to launch into space. Whatever ship is utilized, the space shuttle could carry roughly 20 tons. Mass drivers and space tugs. Anchored to the surface of the NEO to be deflected, they use ion motors for tugs or harvest material from the asteroid itself, mass drivers, to apply a low-intensity but long-lasting force on the asteroid. In this manner, the asteroid's period of revolution can be changed just enough to avoid collision with the Earth in the long run. Solar sails. Solar sails deflect harmful NEOs by using solar radiation pressure to impart tiny yet steady thrust. Because the pressure of solar radiation is quite low, it is obvious that in order to produce the requisite thrust to deflect an object with dimensions between 1 and 10 kilometers in a few years, sails with diameters of the order of 100 kilometers would be required. Solar collectors. This method is similar to Archimedes' burning mirrors technique. In this case, solar sails with diameters ranging from 1 to 10 kilometers and treated with reflective materials could be used to collect sunlight, which would then be directed on the surface of the asteroid or comet, whose material would vaporize when subjected to the extremely high temperatures of concentrated radiation, resulting in a jet of matter and a subsequent thrust. Alright everyone, here's where the video ends. Thanks for watching, and don't forget to like, share, and subscribe.